Revives here, and today I'm here with one of my first few quantum field theory calculations, and today we're going to deal with Yukawa fermionic theory. So what is going on here is that this problem gives us a Lagrangian density that consists of a massive phi-on scalar field. So this is just a scalar field, we call it phi-on, and then we have a Dirac spinor field, free Dirac field, and then we have a coupling term, interaction term between the Dirac spinors, which could represent things like electrons, and the phi-on and the scalar field. So then we consider a scattering of an electron and an anti-electron, an electron and a positron, with the final and initial states written below here. And we need to show that the amplitude of the scattering is given by this. So how do we go about doing this? You can see that this already hints at us that there's a T process and an S process taking place. So what are those? Let's take a look over here. They are called Mendel-Stem variables, and they talk about two particle scattering. So later we might come back over here for a moment, but in the meantime, let's go through the calculation. So in order to evaluate the scattering, we neglect the case where there's no scattering, where the zeroth order contribution. Then we can actually show that the first order contribution is 0, although we won't show that in this video, and hence the next order that we're interested in is in the second order contribution. So if we take a look at the second order contribution, let's apply Wick's theorem. So at the final state, the two interacting Hamiltonians and the initial state, and we expand it out in terms of the interaction Hamiltonian, and then we apply Wick's theorem and contract the operators. So because we're working with fermions, we need to take care of the signs as well. So we have I used the highlighter to indicate the contraction of the variables. You can see that each color highlights two variables, and we can see that the first four over here is the one that we're going to be exploring, and it's quite systematically, quite nicely read. Why did I not color, let's say, this guy and this guy in yellow? Is because the contraction of those two operators yield 0. So these four are the only four operators that these contractions are the only ones that yield non-zero results, and of course there are other contributions as well, but we are not interested in the disconnected Feynman diagrams, so we'll neglect these for now. I believe it has something to do with renormalization. Yeah. So now all the relevant contractions in the first four terms are given here. Okay. So namely we have these four properties, and this is just the Feynman propagator of the scalar field. Okay, so using that, went ahead and copied down that over here, and let's go ahead and whack through the terms. I'll do the first term only, and the rest of them are just as follows, and can be done with a similar procedure. So and especially because it's color coded, it's actually quite nice to see, and so I've decided to do it in batches. So the first term, all of them are grouped together in such a nice way and highlighted nicely as well. So the first term, we have a contraction of B with the this bar term, and that corresponds to the first contraction over here, and that gives us this term. Okay, this term in yellow. And then the second term is the green one, that corresponds to this guy, and that gives us this green guy. Then the third term is the scalar fields, so it gives us the Feynman propagator. And then the pink term is this guy, it corresponds to this guy, gives us this guy, and the gray one gives us this one, and it gives us this one. So you can go through all the algebra. I invite you to pause the video here to check for yourself. So after performing all the contractions, we obtain several terms over here, 4 terms. So those are the ones we care about, and remember to pick up the minus signs where appropriate, because we're dealing with fermionic fields here. So we have to, when we're doing Wick's theorem, we have to use the anti-commutator instead of the commutator. Okay, so now from here, let's go ahead. We have the propagate. Using the Feynman propagator, we expand it in terms of the integral over 4 momentum. So we obtain the following, and we group the exponentials such that they are grouped in a way that they have y and a w in the other variable. You'll see why we'll do that later. So we go ahead and expand it out, and so the exponentials are simply scalar terms, whereas the u and the v, the u and the v spinors, we have to take care of their matrix multiplication, their vector multiplication. So this, you see that we must preserve the order of this u and v. Okay, then with the following, and then if we must integrate above when we want to do the calculation for scattering. So we integrate over 4 position y and w, and we obtain Dirac Delta distributions or functions, and that lets us collapse down the momentum. So we have this Dirac Delta over here, and we have a, and so this is equals to this, and we pick up some factors as well, some constants. So we now have a single integral in terms of k. So we evaluate the k integral simply by substituting in the values. So these two collapse down to a single Dirac Delta function. So you essentially replace every occurrence of k with p plus q. Okay, so we obtain this, and actually it's nice here because this term is the Dirac Delta, and that tells us that the scattering is 0 unless all the momentums are the same. I mean, the initial momentum and the final momentum is the same. So this term gives us a conservation of momentum over here. We see that conservation of form momentum is obeyed even in particle physics. I mean, of course it must be obeyed. So we obtain the following inner product of the spinors, and then we realize that actually the first term and the last term is the same, and then the second term and the third term is actually the same as well. So we pick up a factor of 2, group them together. I put some square brackets to start to match the final answer. Then yeah, and then from here so going back to our calculation, going back to the initial problem of calculating the scattering between the initial and final states, which is the second order scattering is given by this full term over here. We see that we have already computed this part. This is just a constant, so we go ahead and plug this into here, and we obtain this. So yeah, then using the definition of the scattering amplitude, which is given as such, where we have this as a conservation of momentum, then we compare the terms from here and this guy. So we simply obtain that the scattering amplitude is this, and you see that it matches the answer. So draw 2 Feynman diagrams that correspond to these 2 terms. I have not drawn it, but I'll show what they are over here. So as the name suggests, the terms are, the first term here is a T channel scattering, and the second term here is a S channel scattering. The reason why we have T and S, so these are the T and S Feynman diagrams. The reason why we have T and S and not U is because we don't have exchange symmetry over here when we have a electron and a positron scattering off one another. So we don't have the exchange symmetry that this process will allow. So with that, I have hopefully covered this problem in enough detail. I hope that although I didn't go through each step exactly, but I hope that you are able to catch the steps by yourself. If you pause the video, feel free to leave a like to ask any questions, and yeah, I'm very happy to have done my first slightly more challenging quantum field theory spinor putting fermions in quantum field theory calculation. If that's all, have a nice day, and leave a like and subscribe. Bye.